Clock is ticking.
When do we start?
Clock is ticking.
Everyone, how are you doing? My name is, we're group number 8, and we took care of the hybrid geothermal heat pump system. These are my partners, Miguel Freire and Santiago Paz. A small introduction for geothermal heat pumps. The FIU solar house is connected to a geothermal heat pump that extracts thermal energy from the ground to provide cooling to the house, and then rejects thermal energy back into the ground to provide cooling for the house. And for this reason, it acts as a heat source during the winter and as a heat sink during the summer. A cooling tower is an auxiliary heat rejecting device that can be connected to a geothermal heat pump in order to dissipate additional heat. In doing so, it's going to increase the cooling load, and there's two types of commonly known cooling towers: the dry cooling tower and the wet cooling tower. The dry cooling tower the wet cooling tower is a water-to-water heat exchanger that's going to use the evaporation method to dissipate heat, and then the dry cooling tower is a water-to-air heat exchanger that's going to use air, ambient air, and convection to remove the heat. The advantages to the dry cooling tower, which is the system that we did, is that there is no water consumption. This means that it's more environmentally friendly. There's also no location restriction, meaning you don't have to place the dry cooling tower anywhere near a water source. And finally, it's low cost because you don't have to worry about bringing water to a site, which is very, very expensive.
For the problem, the FIU solar house is located in Miami. It's going to have hot climate and humid, and this will affect the heat pump on the 3 hottest months of the year, that is June, July, and August. That's why it's not enough heat will be rejected by the ground loads. To solve this problem, we want to design and incorporate a dry air cooling tower to the geothermal heat pump to balance the cooling load. For our objective, we want to balance annually the heating and cooling load. We want to effectively utilize renewable energy such as wind and geothermal heat, and also to explore potential application of the hybrid geothermal heat pump in residential buildings.
We have, this is a closed loop water circulated through the system. We started with the ground loop. The ground loop goes to the heat pump where the water is heated, and then goes to the cooling tower where some of the heat is going to release to the anode, and then it goes to the coil again, and when another heat goes to remove by a coil. And then the cycle is going again. For the design analysis, we started with the FIU solar house, then we calculate the coolant load. Then we need to know what is the level required to remove all the heat from the heat pump, and then the final analysis, the prototype design, the fine design, and finally the cost analysis.
Okay, so we started out with one of the FIU solar house plans. This is a close-up of the geothermal piping layout. And as you can see in the top left, you have the location of the water-to-air heat pump that's located inside the FIU solar house. And from this close-up, we can determine that the water lines entering and leaving are of a 1 1/4 nominal pipe size with a volumetric flow rate of 8 gallons per minute.
For the cooling load analysis, we use sensible heat, conduction, convection, and radiation. Also, we did some consideration of how many electrical components only 3 people will be living in the house and lighting. For the HVAC load explorer, we use latent heat, humidity, and vapor. On this graph represent the hottest month of the year, that is June, July, and August. And here are the actual results from the HVAC load explorer. June being 27,000 BTUs, July being 25,700 BTUs by hour, and August being 25,500 BTUs.
Now we have the heat transfer online. We started the heat transfer online with first temperature of water leaving the heat pump. The second, the total resistance of the system, and the last one, the total energy required to remove the hand gauge. Just we started with the water temperature in the heat pump. The equation what we used was the Q convention MSCD delta V, and the final temperature is 93.84 degrees Fahrenheit. So we know from the specification of the heat pump that we have a 35.35 MBTU per hour and volumetric flow 8 gallons per minute at temperature reading and 85 degrees Fahrenheit.
The thermal resistance involves the convection, conduction, and geothermal of the medium ground. This is some of the equation, and this is the conduction shape part. The undergroup called resistor, our total length is 2,316 feet. To solve this, you have to have the thermal resistant heat convection of the water, of the group, of the ground, and the cylinder. Also, the total heat transfer from the water.
So based on these specifications, we come up with an initial heat exchanger that we wanted to design. We wanted to choose a heat exchanger that was lubricant and that can decrease the water temperature by 4 degrees Fahrenheit, meaning the water was going to go in at 94 and it was going to leave at 90 degrees Fahrenheit. The reason why we chose a lubricant heat exchanger is because of its unique design and its highly effective heat transfer rate. We were also planning on rejecting 15,940 BTUs per hour and continue to keep the flow rate of 8 gallons per minute. And there are some pictures.
To solve this problem, we used the NTU effective methods, and these are some of the examples of the equation that we use.
So, for the calculation, the objective of this calculation is to find the phase area that we need to, in order to site the heat exchanger. So we started with the total heat rejected by the water, then the mass flow, the temperature leaving of the heat exchanger, and we have the temperature going in is 87 degrees Fahrenheit and going out at 90.84. And finally, this value, 4.44.
Okay, so based on all these calculations, we found a radiator that would meet all of our specifications, including the 4-foot square, because we would have a face area of this radiator from the left, from active radiator, that was going to be 25 inches by 25 inches. However, the price was extremely high at $1,650. So we decided to come up with a prototype, and we were going to make this. We bought this radiator for $50 from Sunbelt Radiator, which is a local company, and it was going to reduce 2 degrees Fahrenheit. And we were planning on buying 2 of these radiators so that we could put 4 gallons per minute in one radiator, 4 gallons per minute in the second radiator, and we were going to make it into a V shape inside the cooling tower.
So for the fan design analysis, we have 3 considerations. First one, centrifugal fan, ancient fan, and crossflow fan. So we choose to have a crossflow fan. The crossflow fan was chosen because there is a very low cost, even though it has tend to be more lower than the ancient fan, centrifugal fan. But the problem is that the heat pump, the cooling tower will be installed outside, where the fan, where the loader is no a problem. The second analysis what we did, it was the fan performance table. Using the fan performance table, it's easy to make an initial selection. However, it relates pressure, efficiency, volumetric flow, and power. But what happened? Due to the lack of this table, we had to do 2 experimental data. We choose a 3-4 electrical motor, and then with 4 speed. So we taste every blade. We taste 3 different blades, and we measure the current of from the motor specification. We have from the first column, we have a reading of 3.2, the second one 7.5, and the last one 8.8. What we did, we choose the second one because the first one is too low, and the last one is too high for the specification of the motor. Next, we calculate the velocity in order to find the volumetric flow of the rate. So we calculate the velocity using the pilot tool. The pilot tool is an instrument to measure the total pressure and the static pressure in a flow. The result of the 4 different speeds, we see that the first speed has a 72.87. The second one, 4,055. The third one, 4,911, and the last one. So we choose to have 4,055 cubic feet per minute.
On our design, we have 2 designs. The first one was a 25 by 25 radiator. This one was a custom-made radiator. Also, the motor is going to be horizontally. This one was a little bit heavier and a little bit too wide for our project. So we did the second design. This one was you're going to have 2 radiators. It's going to be 13 by 13. They're going to be in a V shape. The motor is going to be vertically, and this one was going to be more compact.
Okay, so we have the specifications for the frame housing design. As you can see in the top right corner, we have our frame with the hinges in the back and in the front to sustain the radiators at an angle of 60 degrees. And we were planning on making the radiators. We were planning on making the cooling tower as compact as possible by placing the radiators as closely as possible. And we also wanted to use an aluminum bars of 1 inch by 1 inch cross sections with a shell thickness of 1/8. As you can see, our length is 28 inches, our height is 28 inches, and our width is also 24 inches. And the 2 bars on the top are to sustain the motor. Some of the extra features that we incorporated into our cooling tower is a Type K thermocouple, the thermal controller, and the shutoff valve. We have the cooling tower system process. Here's how all the components are going to work together. You have 4 components that are working at the same time. You have the thermocouple, you have the Omega thermal controller, the shutoff valve, and finally the dry cooling tower. What's going to happen is that from inside the solar house, there's a heat pump, and the water is leaving the heat pump at 94 degrees Fahrenheit. The thermocouple is going to read that temperature, the water temperature, send that signal straight to the thermal controller, and the thermal controller is going to send out 2 more signals. The second one is going to be to the shutoff valve to redirect the water to go towards the dry cooling tower, and then it's also going to send third signal to the actual cooling tower to the relay of the motor to turn on the fan.
For the total cost analysis, we have 2 designs. The only thing that is changed is the heat exchanger. Like I said, from design 1, it was a custom radiator from active radiator that cost $1,650, and from Sunbelt that it cost only $50. We should design number 2 because it was cheaper. It was only $1,000, and we save a money of $1,659.
So here we have a small demonstration of our cooling tower, the final prototype testing. As you can see, it's not working, but basically we have the ambient temperature of 80.8 degrees Fahrenheit at the top left, which you can see with the digital thermometers that we use. We're testing the medium-low setting so we can have a flow rate of 4,000 cubic feet per minute. And we were expecting for this cooling tower, which is this one right here, to decrease 4 degrees Fahrenheit, but that didn't happen. It actually reduced it by 7.6 to 8.3 degrees Fahrenheit. And we know that it's because of the cooler ambient temperature. We have 2 approaches for implementing this cooling tower. The first one is to use this cooling tower and place it right now with the FIU solar house and to not remove any ground coils at all. This means that we'll set the thermal controller to 94 degrees Fahrenheit, and we're going to be balancing the annual cooling load 1/4 of the year, meaning the three hottest months of the year, June, July, and August. The second approach is to remove a substantial amount of ground coil and replace it with the cooling tower. By doing so, we can set the thermal controller to 90 degrees Fahrenheit, and we'll be balancing the cooling load for more than 3/4 of the year.
So we have the analysis of the coil removing analysis. So we can see if we choose the cooling tower to release 0 degrees, that's no length to be removed. If we say to 90 degrees, it's going to be removed 261 feet of coil. And so on until the 4 degrees that we're looking for, that removed 1,044.48 feet.
This is our timeline. Since the beginning of the semester, we have started working on report number 50%. Also, we did our device testing, our assembly our device, and we did our planning and all the final reports. For global learning, we're going to put some warning labels. Probably it's going to be a manual book in English and Spanish or different languages. And also the geothermal energy is mostly found in the Pacific Rim.
Those are the 2 warning labels that we placed, and they're in the cooling tower. Thank you very much.
All right. Are there any questions? You think if you doubled the size of the radiators, you could go to 14 degrees? I mean, from your experiment, you started out with 4, you got 7.
Yeah, our initial.
If you made bigger radiators, the logic would then be.
It was definitely a surprise. We tested the initial specifications for our heat exchanger was going to be 4 degrees Fahrenheit, but the day that we tested it, because it was a cooler day outside, it was 80 degrees Fahrenheit. This is meant to be tested during the hottest months, June, July, and August, to see its efficiency. However, we're not there yet, so we're planning on testing it in the later on.
At 92.
You're right, with the hotter temperatures.
Okay.
You said this prototype was designed primarily for residential.
Yes, yes.
Now, what's it gonna cost a homeowner to
Okay.
purchase?
Well, we have an example that we wanted to show you with the FIU solar house savings. Basically, we don't know how much the geothermal heat pump cost to be installed in the FIU solar house, but we're assuming that the ground source heat pump costs $15,000. And from the $15,000, $3,000 went to the heat pump, and $12,000 would go to the ground loops. What we want to focus here is on the ground loops. Here I'm including the labor, the excavating the ground, installing the system, flushing it, all the works. Our cooling tower is going to cost $1,009 plus the installation, a total of $1,205. That number is never going to change. Based on the ground loops that cost $12,000, and based on our calculations that we have underground, we have 2,316 feet of underground loops. And in total, it would cost $12,000. It means that for 1 foot, it would be approximately $5.18. Again, this is an assumption that the ground source heat pump would cost $15,000. So this means that our cooling tower would remove 4 degrees Fahrenheit. Based on our entire analysis, for 4 degrees Fahrenheit, we can remove a total of 1,045 feet of ground coil. By doing so, the extra 5 degrees Fahrenheit are going to be removed by the new ground coil, and that's going to be an amount of 1,271 feet, and is going to cost $6,589. So meaning that for the cost analysis at the bottom, a ground source heat pump installed by itself would be $12,000. The hybrid ground source heat pump would cost $7,794 for a total savings of $4,206.
And currently, there isn't any in the market for the residential areas. Is that true?
Right, we want to, I'm sorry, I don't understand.
Well, I mean, right now it's mostly for industrial areas.
Yes,
Right,
yes, it
so
is.
there's anything comparable for the residential areas.
Right,
So you can make any sort of comparisons as far as what the cost is for residential areas as of now.
right, right.
How deep are those ground coils and that depth? Does that consider the on-the-ground environment of South Florida, with high water table and all of that?
Absolutely, absolutely. If you want to do a vertical loops, you would have to dig more than 100 feet. And they go anywhere from 100 feet to 300 feet. And then that would be a closed loop system, but you would be hitting water down in South Florida. And that would be very expensive. That would be more expensive than the horizontal lay loops. Horizontal lay loops are usually laid out about 6 feet underground. That's the FIU solar house is laid out. The slinky loops are horizontal, and they are laid out 6 feet underground. Horizontal loops are a lot less expensive than vertical loops because the trenches don't have to be very deep. You don't have to dig them very deep. But this would save money in either case.
Any other questions? Hearing none, seeing none, thank you so much. Well, that concludes our morning session, our